Our microcontroller and embedded system, Module 5, Session 6. So we will discuss today what is RPC, Remote Procedure Call. So previous class we had discussed a few concepts in inter-process communication, that was sharing information or communicating within two processor or between two processes with the help of shared memory concept and also with the help of message passing. And in those methods, we never assume that the processes which were meant to be communicated uh, existed. We assumed it was present in one system. Rather, in this method, we will assume that there is two systems and one process belonging in one system needs to communicate with another process which is belonging in second system. This is actually one major difference when we talk about RPC call with respect to other methods which we had looked at during IPC. I repeat, remote procedure call. In this case, there will be two systems and one process belonging to one system or one machine wants some information or services which is present in some other machine or some application. Okay, so you can consider it as a try client and server model, wherein if you require a service present in a server, client definitely has to pass a request. Upon receiving the request, the server, if it's a genuine subscriber, probably the server can give the information back to the client. Okay, and so to make this possible, what and all are required, that's we will discuss here. And mainly RPC is used in distributed application like client server application. Hope you are aware with this client server application. I had repeated it again, let me repeat it. So in client server applications, the applications which your server requires could be a web application. The application which the server requires would be uh, accessed. Client is the one which is going to provide request. Upon receiving the request, the server would give the service back to the client. Okay, so here remote procedure call and procedure call, there is a difference. So it's something like you're calling a function. Remote procedure call implies you're calling a function which is existing in some other machine, whereas a procedure call is your one program is calling another program. So you call normal procedure call, but both are located in the same machine. Whereas in remote procedure call, remote implies here it is a server. So you're fetching some service existing in the server, and who requires it? Client definitely requires it. Okay, and the server might use different operating system here, and the client may use different operating system. So in this case, how the communication happens when you're using a heterogeneous network is the one as I address now. Client and server application both are running in different operating systems. Okay, and we call server and we call client as one. So CPU or process, you can call it as a process containing the procedure which needs to be invoked remotely is known as server. Okay, the one which requires the service is known as client, and the which has the service, the one process which has the service is known as a server. Okay, in to make the process communicate with each other, then RPC does what? Let's discuss that. Okay, so this is the pictorial diagram of RPC. So you have a process and you have a second process. This is one process belonging to one system, and this is one more process belonging to another system. Now suppose if this service is required by this process, this service, in the sense this is a process, so this is different machine, this is different machine. So then first what it has to do is it has to provide a request. So for providing a request, so you might think, you might come to a conclusion that how does this find the address from where it has come. So there is a concept of a socket which basically is used for establishing the connection between the client and the server. So if the client has to transfer information to the server and server again providing the service and giving it back to the process, there needs to be a kind of a connection which needs to be established. For making this connection possible, we'll be using a concept known as socket. So socket is the one which makes this connection happen. Okay, and socket you can consider as kind of a end points which is attached to a systems. Okay, so you have one process running in one machine, you have one more process running in second machine. This socket would have a IP address. Along with that, you will be having a port number. So similarly, this socket related to the server will also have its own IP address, and you will be having a port address to it. So together you have this will be become your socket information. So this is the way via which the connection will be uh, created between the client and the server. So here 148.86.5.20 happens to be the IP address of your first machine, which has a process, and that process requires the process belonging to the system. And in that case, if since it requires some information, so it will attach a random port address. This port address will be supplied by the host machine. This machine is going to attach this port address, and using the secured call it as a whole address, the data goes through this mode. Okay, and when a client process initiates the request for a connection, it is assigned a port by the host computer. This 1625 is actually the port which is assigned by the host computer, and this port number has to be always greater than 1024, because many of the ports are meant or used for some standard application. For example, 80 port is used for HTTP. Telnet uses port number 23, if I'm not wrong. So all those are meant for providing standard services. Could be a HTTP response, file transfer response has its own port address. So port address cannot be lesser than 1024. So it should be always greater, due to which this number is added here. Okay, the packets traveling between the hosts are delivered to the appropriate based on the destination port number. So here, through this 80 port, all information is going to be retrieved from this uh, you know client. And suppose if it's its own dependent or its genuine subscriber, then probably it can accept. Once it accepts the request from the client, then the services from the server could be passed back to the client, whatever the services this is requesting. So if it's a genuine subscriber, if not, probably you can block the request. So it's possible to make it more secure. Okay, so as address sockets, it's a logic endpoint. So whenever you want to communicate between a server and client, then you can make use of a socket which will be having a IP address as well as a port number. Okay, and that's to ensure that from how the data needs to be transferred from one end to another end. Okay, and the inet socket, and you have one more socket named as Unix socket. In inet socket, you can use a connection oriented, or you can use a connectionless. So if you are using connection oriented, then you can move with TCP IP protocol, and if you are working with connectionless transfer information, then you can use UDP always protocol. So stream socket implies it is a connection oriented, datagram socket implies it is a connectionless. So here you will be using UDP, and here you can make use of TCP protocols. So that's about task communication. We will talk about the next concept, which is task cross synchronization. Okay, in task synchronization, let's discuss what basically task synchronization is and why it is required. So consider a situation that there are two processes, namely P1 and P2, and this two processor is going to use a common memory, and it is trying to access it at the same time. One process might try to modify the content present in the memory, and one more, its job is just to read the data. Now let's assume that P1 would access a memory region starting from 1000, starts from 1000, and it tries to change the value present in the location 1000 to 2000, and let's assume that the access time is same. Okay, so it one by one memory location it will search, and it will try to access the content, and it will change the content as well. And assume that the same time the process 2, assume it starts from the location 2000 rather than 1000. So from 2000 to 1000 of the same memory region, it tries to read the content. So initially there is no hiccup as such, because 2000 is the final address there. The data is same as it is. It starts moving up in the up direction, as well as process 1 will start moving in the downward direction. As soon as you reach 1500 memory address, you have a inconsistent data now, because if we assume that the process 1 and process 2 are sync, when we say sync, this access time of this two processor to access the memory information is same, then definitely when once you reach 1500 memory address, you will not be having issues. But when you go on to 1500 above address, okay, then you have a problem to deal with. In that case, almost all the contents above 1500 to 0, almost all are been inconsistent data. The expected data by process 2 might be different, but the process 1 has already traversed this region, and it might have destroyed the content. So definitely there is a data inconsistency. Now, how do you solve this? This method of providing the synchronization between process to ensure that you don't have a data inconsistent problem is nothing but task communication. So task synchronization ensures that it will make the process, if two processors are using the same resource, so it will tell the one more process which has been probably you can think as if it's been given less priority. It says that one process is already using this resource, wait for a while. So doing so, to some extent, data inconsistency could be avoided. Okay, so that's the work of the task synchronization. So just to so the act of making process aware of access of the shared resource by each process to avoid conflicts is known as task process synchronization. So suppose if one process holds one resource, and second process requires it, just tell that it has been already occupied, or it has been already reserved. So later a while, when the process 1 releases that resource, the process 2 can use it. So in that case, you can try to avoid this conflict. So the in same resource may have same data even after processing. Okay, so under this, the issues, common issues under task synchronization, we will discuss two issues. One is a racing. What is racing? We will discuss with the help of this program. The program has a common memory. We will assume that this buffer of 10 is a common memory, which needs to be shared by the process A as well as process B. So process A and process B are using a piece of code which is something like, it will check whether the content present in this buffer is greater than 10. So definitely when you look at this elements, all are having a value greater than 0. So each time this execution happens, the counter value will be incremented, and you will be calling that process once one process, if it's involved. So this will be executed. So first five information of this variable buffer variable will be grabbed, and the counter would become 5. Then when process B is called again, from J, from 5 to till it reaches 9, 0 to 9, because so it will be looked at and it will be compared with 0, and it is greater. So again you are going to change the value of counter. So ultimately we expect the result to be equal to 10 when this program executes. Now let us discuss what is racing. So when you try to use this variable, so the counter is a variable which will be shared by these two processes. Definitely you will be sharing the buffer value also, but this counter is the one data which you are going to modify. You are altering in process 1 as well as in process 2. Okay, so simultaneously when process A is executing the program, and at that time process B, if it's been enabled, then you have a problem to deal with. The count which has to be incremented may not get incremented. We will talk about why this happens. Okay, so before that, hope the program is okay. So you have concept here, the race condition. So as addressed, race condition is a situation in which multiple process, they compete with each other. So here the process where process A and process B both try to take this counter. Okay, the counter is a variable which it tries to access and manipulate. So if the counter value is 0, and if the counter was not changing in process A and process B, then you cannot think as if this is a racing condition. But now both are trying to modify the counter value. Okay, and in C++, when we write C or C++, you write counter plus plus. Counter plus plus is a single instruction, you think, but when you decompose this, when you translate this into a machine level language, so you use 3 instructions to execute this one single line. So counter is one variable which is located in some memory address. So using the pointer in machine level language, how this gets transformed into 3 lines. So what is this? You have a command here, move EAX. EAX is your accumulator, and pointer EBP minus 4. So get the data, you call this as load the counter value, whatever the value counter has, using the pointer, which we call it as a base pointer. Okay, using the base pointer, access the data present in counter initial value, increment it by 1, and store it at the same location. This is what basically the counter plus plus does when we think as if when we translate this into assembly code. Okay, so this is the situation. Then the process A counter plus plus would look something like this, and process B counter plus plus will also have the same command. Okay, now let us look at the situation, what happens if this scenario takes place. So in this scenario, you have say that counter right now is almost four value it has executed, and it is expecting 5. But when you're using counter plus plus, at that time assume that process B is enabled. So when process B is enabled, and when you're at this line, and there should be a switch to process B. Process B set of instruction should be executed. So you were down the line here, the counter value is will get modified only if you perform add instruction. Okay, because this 3 line of code is equal to counter plus plus. So when you're down the line over here, there is a context switch. So process B is enabled now. In that case, again, the instruction starting from the for loop and it compares with 0 will happen, and finally it will use this count plus plus. So here till count from 0 to 4. So 4 you might have reached, but later simultaneously parallelly process B is called without shutting process A. Okay, so in this case definitely there is a problem to deal with. So the expected answer is different, and here add EAX comma 1, when you try to do the address, it will not get the proper address, because this move D word pointer EAX, it is incremented again. You're trying to increment it, so there is a data inconsistency due to which the expected answer 10 may not be 10, it might be different, it might be sometimes 11, could be different also based on the situation how this is formulated. Okay, in this scenario it will not be 10 if two processors two processes runs simultaneously. So this has to be avoided, or this can be discarded by saying that if process A is running, try to ensure that process B counter it will not get. Okay, this memory or variable counter at any cost, process B will not use it when process A is handling it. So in this way you can avoid this racing condition. So it can be done with the help of operating system would try to ease up all this. So there are many methods, task synchronization methods, which is not there in the syllabus. So hope this concept is clear. What is racing? Racing means trying to access a common data. Global variable could be by by multiple processors concurrently at the same time. Ensure that the two processors works at the same speed. Okay, and the next concept, task synchronization issue. One more issue for task synchronization happens to be a deadlock. Deadlock you can think as if by looking at this pictorial diagram. So this is actually the you have four lanes, and all lanes the traffic is busy and it cannot go. This probably vehicle cannot go to this lane because it's completely jammed. So traffic jam is actually the scenario in real life which we can anonymously relate it to a deadlock condition. Okay, so deadlock is a condition, computer science terminology. It is a condition in which one process waits for a resource which is held by another process, and similarly that process might require a resource which is held by the first process. Okay, for example, assume you have two processes. Process A is holding one resource which is X, okay, and it wants resource Y. Similarly, process B is holding the resource Y, but it wants X. So in this case it's completely traffic jam, right? So because as addressed for eliminating task synchronization, you have to ensure that if one process is holding one resource, then unless and until it voluntarily releases that resource, some other process cannot use. Multiply or concurrently one more process, when someone is using one resource, that process cannot use it. Okay, so this is a scenario of deadlock. I repeat, process A holds resource X, which means when it is holding one resource, process B cannot access it, but it wants it. At the same time, this is also holding one resource which this requires. So this is a concept of deadlock. So that's explained here. So in this case there is a complete hiccup, and the data will not be moved at all. So definitely process B, it actually requires resource X, but it will not get it. Similarly, process A requires Y, but definitely it will not get because process B is having it and it will not release it. Okay, and these are actually some of the scenarios under which deadlock arises, or some of the condition favoring deadlock. So one is mutual exclusion. Mutual exclusion is, you might have come across mutually exclusive events. So event which is independent. So here we mean to say that the process can hold one resource. The process holds a resource at one time. Okay, this process which is holding a resource cannot be shared by some other process. Another process cannot use this resource. Okay, so since due to which to some extent there will be a deadlock situation later while, but this one condition is not fair enough. Along with that, there are three more conditions which should also be occurring, so to make it deadlock. So second one is hold and wait. This already we have explained, the condition in which one holds a resource and it locks the shared access, waiting for additional resources held by the other processes. So this holds one resource and it has been locked, and it is waiting for some other resources from some other processes, which if those are also locking their own resources, then definitely this will also not get that resource. And no resource preemption. So no resource preemption is a process in which operating system will not get involved to make the resource release. If process 1 is holding, the process 1 itself has to voluntarily you know release the resource which it was holding. So there is nothing involvement with respect to operating system. So no resource preemption, no priority whatsoever. It's not something like robin based. The processes will release its holding state. So it has to be done completely with the help of a process itself. The final one is circular wait. So this is also a condition, something like a process is waiting for a resource which is currently held by another resource, and again that particular which is held by another process, and that process is also holding one resource which is expected by process one. So this continues a kind of a circular wait. All are in wait state, but there is a hiccup, nothing moves as such. So when all this conditions are clubbed together, you get a deadlock situation. So these are actually some of the concepts which favors deadlock. Okay, so time being we will stop here. Next we will discuss the other methods in